Welcome to today's lesson, beginning on page 12 in your notes. And this topic here is called concavity. When you have a curve can be concave in one of two directions. If it's concave down, well, here's your two diagrams right here. If a curve is concave down, let me get my pen, then it looks like this right here. You can tell if a curve is concave down because you have to take the second derivative, not the first. You take the second derivative, you plug in any point that's on a region of a curve, and if you get a negative value, meaning if it's less than 0, then it's concave downward. I'd also like to point out that if it's concave down, in other words, if the second derivative is negative, then it will have a relative maximum point. Okay? And here's what a curve looks like if it's concave upward. It's like a parabola that opens upward everywhere. The second derivative in this case will be positive. It'll be greater than 0. And if you have a curve that's concave upward, in other words, if the second derivative is positive, then you get a relative minimum value. All right? So negative would be a max. Positive would mean you're going to get back a min. This is called the second derivative test. It's just another test that you can use as opposed to the table of increasing and decreasing values as we were using in our last lesson. So we're going to do this test today. I'm going to show you how it works, the second derivative test, to tell if something is a maximum or a minimum value. And it is the standard test. It's the one that's usually used. Okay, so this is what we mean by the second derivative test for maximum and minimum. If you take the first derivative and set it equal to 0, you'll get a certain value of a. Now all this is saying is that a is what we call a critical value. And the same thing here, a is a critical value. We saw critical values in our last lesson. So if you have a critical value, you know it's either a maximum or a minimum. You put that critical value into the second derivative. If it's less than 0, that means you have a maximum. If you plug that critical value into your second derivative and it's greater than 0, that means if it's positive, then that means you have a relative minimum at that critical value. This is a beautiful little test, and we're going to be doing that in our example on the next page. Okay, what about an inflection point? What do we mean by an inflection point? Well, let me just go back for one moment and look at these two curves right here. Now we know that these curves, one of them is concave up and the other one is concave down. Well, what would happen if you had a piece of curve that was concave down, such as the above piece, but what if it led into another curve that was concave upward like so? Now, if you look at this piece right here, there's a section that's concave down from about here to about here, and then there's a section that's concave up from about here to about here. Well, the point where it changes from concave down to concave up, or vice versa, the point where it changes direction, that's called right there the point of inflection. And that's another important point that we're going to learn how to calculate here today. It has to do with the second derivative. All right, so that's an important point. You'll be including that on your graphs as well. And here is where you can tell where the inflection point occurs. Inflection points occur where you take the second derivative and you set it equal to 0 and you solve for your x values. Something like the test for critical values. But the critical values, you had the first derivative set equal to 0. For points of inflection, you take the second derivative and you set it equal to 0. Okay, so let's have a look on page 13 and see what we have right here. Now, this is just a very simple example. I'll fill in the blanks here with you just to show you what's done. But it says, consider the graph below. And you can see it's almost like the one I just drew on the previous page. Now, from I, which is right here, to B, which is right here, what does it look like that section of the graph is? Well, it looks to my old eye like it's concave upward. It's concave up. All right. In other words, if you plugged in any x value on that whole region, right from I up to B, if you plugged in any x value into the second derivative, you'd get back some positive number, right? Because it's concave upward. And of course, there's your minimum, right? Concave up means it has a min. From A to I, well, what would you say? From A right there to I right there, it looks to me like it's concave downward. Okay, concave downward. M right there is a relative maximum, because it is a max, but just for that small piece of the graph. There's pieces of the graph that's actually higher. Little m is down here. That is a relative. I apologize for my pen. It still leaves a lot to be desired. So that is a relative minimum right there. I, now look at I. There's the point I. That's the point where your graph changes from being concave down to being concave up. And that means it is a point of inflection. That's a point of inflection right there. And like I say, it's a point that we're going to be including when we start sketching the graphs in our next lesson tomorrow. So here's the only example that they have now. This is on page 13. So what I'm going to do is I'm going to answer the question that they've got here. It says determine the concavity. Well, that means, everyone, you're going to have to tell where on that graph is it concave upward and where is it concave downward. That's going to require a table something like the table we did last day for increasing and decreasing values of a function. All right, and find any points of inflection. So I think that's what we should do first, because the points of inflection is going to indicate what values do we put into our table to determine the concavity. So let's go. We'll take the first derivative. Y prime is equal to 3x squared and then minus 3. Now that's the first derivative. Remember, if you wanted to find out where your maximums and minimums were, you'd set that equal to 0. And I'm going to do that with you in just a moment, just to show you how this test for concavity works, or how the test for max and min works. Second derivative test. Now, if you want the points of inflection, you need to find the second derivative. So the second derivative is 6 times x, 0. And that's it. That's your second derivative. So we set this equal to 0. We set this equal to 0. And you've got a pretty simple equation to solve here. 6x equals 0, divide both sides by 6. You get x is equal to 0. Now, do I need to find the y value? Well, yes, I do, because they're asking for the point of inflection. So all you need to do is take that value of x, which is a 0. It's a pretty simple calculation. Plug it back into the original function right there. Right? So if you put in a 0 for x, you're going to get 0 cubed minus 3 times 0. So that gives you 0. So 0, 0 is the point of inflection. I'll just put down P. POI for now, because I'm having trouble with my pen. So POI, there's your point of inflection. So we have this part done. We have found the point of inflection. But now, what about the curve on either side? Is it concave up or is it concave down? I have not determined that yet. And that's where I would require a table, much smaller than the ones you were using in the last section. But here's your table. All right, you're going to have columns like this. And now, because there's only one point of inflection, you only need 3 columns in your table. You only need 3. You put the actual x value for your point of inflection, which is 0, right there. That goes right into the middle column. So you put your 0 in the middle. Remember, now this is your x value. Okay, that's your x value. You're going to pick a number or a little bit smaller than 0 to go in the left column. So like -1 would be fine, just like we did with the table yesterday. Pick a number a little bit bigger than 0 to go to the right side, okay, like a positive 1. But now, instead of using the first derivative here in the middle row, you're going to use the second derivative, because it's the concavity you're concerned with. Okay. Now I know the concavity at the actual point of inflection at 0, 0. That's going to be 0, so you don't have to worry about plugging that in. You know that's going to be 0. That's not concave up or concave down. So you don't need to put anything right here. You can just leave that blank. Put in -1 into your second derivative. Now remember, here's your second derivative. There's your second derivative right there. So if you were to put in -1 there, all you're going to get is 6 times -1, and that's -6. So that's a negative number, which means that this part of your graph is concave down like a sad face. Always sad. But now you'd get a maximum there. All right, somewhere in that region. If you plug 1 into your second derivative, you get +6. So that's positive, obviously. So you're going to have a section of your curve, that's concave upward. And that's all you have. There's just one section that's concave down. There's one section that's concave up, separated by the point of inflection in the middle. So now to answer the question, to determine the concavity, here's what you would have to say. Concave down. All right, well, where? Where is it concave down? Well, from 0 and to the left. All right, so I would have to say x less than 0, because 0 is where the point of inflection occurs, remember. Concave up. Well, that would be this piece of your curve, right? From 0 upward. So I would have to say x is greater than 0. And this statement, these two statements, I should say, they answered the question, determine the concavity. Under which intervals is it concave up and which intervals is it concave down? A table is required for use right there. So now I'm going to erase that because I have just maybe about 3 minutes left. I want to show you how the second derivative test works. Now, it's much easier than actually using the table like we did in our last class. So I'm going to erase this and this and this. I'm going to erase a whole bunch of this stuff here now. If you didn't get a copy down, remember you can go and look at the, I should have left that second derivative there. If you didn't get this copy down, you can go and watch the video again, because all of these are saved. All right, so erase, 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 erase. I wish there was a quicker way to do this. There probably is. Okay. All right, so watch what I'm going to do here. Now, what if you wanted to find the maximum and minimum values? The question doesn't ask you to do that. All right, but I'm going to do that because I feel like doing that. All right, so here we go. If you want to find the maximum and the critical points, you use the first derivative, which we've already got right there, and you set that equal to 0. So 3x squared minus 3 is equal to 0. So you can factor out 3 in front of x squared minus 1 is equal to 0. Remember, now you're solving this, and by the way, that's the difference of 2 squares. So fortunately, you can factor into x plus 1 and x minus 1 equals 0. So, of course, now 3 will never equal 0. That's not going to give you a solution right there. But the x plus 1 equals 0 means x equals -1. And the x minus 0 means x is equal to +1. Now, I'll tell you what, let me just plug those back into the original function to get the y value. So I'll actually give you the points here that are max or min. So if I plug in -1 here, you're going to get -1 plus 3. So I'm pretty sure you're going to get a 2. -1 and 2. All right? And if you plug 1 in, you're going to get back -2. So there's your 2 points. Here's 1, and here's the other. Now remember, you know they're critical points, but you don't know if they're max or min. So here's what we call the second derivative test. And it's much shorter, much easier than using that big table like we did in our last class. So I've got about 1 minute left. So the second derivative is, well, it was just 6x, wasn't it? That was easy. So you take the second derivative and you plug in -1, for example. So if I plug -1 into the 6x, I get -6. So that's less than 0. It's concave down. So ta-da! There you go. That's a max. So I know that the -1, 2 is a max. Plug in +1. That's my other critical value. I get +6, which is greater than 0. So it's concave upward. And by golly, therefore, it's a min. So that's how you use the second derivative test to determine if a critical point is a max or a min. And you don't need to have that table like we used in our previous lesson yesterday. Okay? So I'm going to stop there. Tomorrow we're going to actually put all of this together and start graphing some of these functions. I'll be using the second derivative test then as well. And if you can get your hands on some graph paper before then, could you please do so? Anyway, I'm almost out of time. I will see you tomorrow. Have yourselves a wonderful evening. Bye-bye.